Welcome everyone. Let's give folks a minute or two, then we can start. All right, so we are at 12 o'clock and we have a bunch of attendees and people are still trickling in. We can get started with some introductions here. So welcome to Sentinel Innovation and Methods webinar series. My name is Rishi Desai. I am an assistant professor here in the Division of Pharmacoepidemiology at Brigham Women's Hospital and Harvard Medical School, and I will be moderating this session. US FDA Sentinel system, as many of you know, help address questions related to safety and effectiveness of marketed medical products. The Innovation Center focuses on developing innovative methods to further advance Sentinel by leveraging new data sources, building new tools, and enhancing real-world evidence capabilities through advanced analytics. We launched this webinar series to engage with experts and innovators in key areas related to the Innovation Center's master plan and Operation Center's methods work. And with that, I'm very pleased to introduce today's speaker, Dr. Brian Shefford. Dr. Shefford is a professor and vice chair of faculty affairs in the Department of Biostatistics at Vanderbilt University. He's a fellow of the American Statistical Association, and his statistical research has been in the areas of causal inference, observational data analysis, and methods for ordinal analysis. Most of his research applications are in HIV and global health, and the topic that he is going to cover for us today is based on his paper that he published with several co-authors titled Multi-Wave Validation Sampling to Improve Estimates Derived from EHR Data. So this is something that we care deeply about at Sentinel, where we are interested in validating the endpoint definitions or outcome definitions that we use from EHRs or claims data sources. So we are very much looking forward to hearing Dr. Shefford talk about his experience and this really elegant work. Before getting started, I would like to mention that all of your lines are muted. If you would like to pose a question, please type it in the Zoom question answer feature, and we will get to all the questions at the end. Finally, this session is being recorded and will be made available publicly through our website, which is sentinelinitiative.org. And with that out of the way, I will hand it over to Dr. Shefford, and again, thank him for joining us and sharing his expertise with us. Brian?
Thank you, Rishi. I really appreciate the introduction. Can you hear me okay?
Yes.
Yes, great. Well, I'm going to talk to you today about data quality and statistical methods to address data quality. And like Rishi said, I'm pretty much going to follow a paper that is currently in press at Biometrics, a multi-wave validation sampling for error-prone electronic health records. And I just want to start by acknowledging my co-authors on this. Pam Shaw is the co-PI with me on the grants that have funded this work. She is at Kaiser Permanente, a biostatistician, been a wonderful colleague to work with. Bill Hierman is a pediatrician who's at Vanderbilt. The application we're going to be talking about today is looking at childhood obesity, and he's been very instrumental in guiding us through the science of this project. Thomas Lumley is a statistician at University of Auckland in New Zealand who has expertise in statistical sampling and also computation. Stephanie Duda is a biomedical informatics professor at Vanderbilt who's done a lot with data validation and also with REDCap. And Shannon Pugh is a research nurse who did all of the chart reviews I'm going to show you today, which was a lot of work. And then Aihua Bian is she's a biostatistician at Vanderbilt. She's been our data manager. Tong Chen and Kyung-hee Han are both recent PhDs in statistics or biostatistics who helped with some of the analyses, and then me, of course. And I just also wanted to acknowledge real quickly Gustavo, Rand, Sarah, and Mark, who are people that are working with me on similar problems, and a lot of my thinking has been influenced by them. And they're all at Vanderbilt, or they were at Vanderbilt, and I'm grateful for them. So routinely collected clinical data, including electronic health records data, are increasingly used as a data source for medical studies. And they're great. It's possible to get lots of data on people very quickly, but it's being more frequently recognized that these data are prone to errors and there are potentially problems. In fact, data quality has hit the mainstream media. This is something from the BBC. It came out in February of 2021, which is right when the COVID vaccines were being rationed. And I'll just read it to you. It says, COVID, man offered vaccine after error lists him as 6.2 centimeters tall. A man in his 30s with no underlying health conditions was offered a COVID vaccine after an NHS error mistakenly listed him as just 6.2 centimeters in height. Liam Thorpe was told he qualified for the jab because his measurements gave him a body mass index of 28,000. He told BBC Radio 5 Live, quote, I put on a few pounds in lockdown, but I was surprised to learn that I made it to clinically morbidly obese. It really made me rethink what I was going to do for pancake night, end of quote. I like this, Liam Thorpe. Now, I have confidence that our data managers and our statistical teams, the people I'm working with, would catch this sort of error. But there are lots of errors in electronic health records that potentially that are not easy to catch with data, with computation queries like what we would do to catch this sort of thing. And sometimes those can have a big impact on results. Here's an example, a paper published in JAMA in 2012 by Floyd and colleagues. I don't know anything about the science behind this, but they're looking at incident rate ratios for statin-related rare drug adverse reactions. And essentially, the bottom line is when they used unvalidated data, they got essentially a null association or very weak association, whereas after they validated the data, they got very strong associations. So it really changed the science by validating their data. And I've seen this also in my own research. I mainly do global health HIV research. This is data from our local Vanderbilt HIV clinic. And this group, they've spent a lot of time and money validating all of the key variables used in analyses for their studies. And so we can look at the data that was extracted directly from the electronic health record, and then we can compare results to what we got after we validated all the data. And in some cases, we get things that are quite different. So this is an example looking at the incidence of AIDS-defining events after starting antiretroviral therapy. And the incidence is quite a bit higher using the unvalidated electronic health record data than it is after going through the charts and validating. And if we look at the association between CD4 count at baseline and an AIDS-defining event, the association is much stronger using the validated data than it is using the unvalidated data. Now, it's often impossible to validate all records. It takes a lot of money, a lot of time. It's often unrealistic, especially with really large data sets. So an alternative is to validate data on a random subset of records. And the goal is to obtain estimates that are efficient, so narrow confidence intervals, but are close to estimates that we would have gotten had we validated the entire data set. And so our large research agenda has been three main components. So one of them was estimation. So how do we best combine validated data on a subset with the unvalidated data on a lot of records? Design is how do we best select which records to validate? Some may be more informative than others. And finally, applying these new methods and designs in practice. And so this talk is going to go over a lot about the application in practice, but I want to give you just a little bit of a sense of what we've been doing for estimation design, these first two components, before we get into the application. So the basic idea is, it's here in this picture on the right. We have electronic health record data on a large patient population, and we validate it for a subsample, a small sample. And we want to somehow combine this data with the larger data to get estimates that are unbiased, but are also more efficient than if we just analyzed the fully validated data itself. So there are traditional, so this is a setting where we have errors in variables. And so you can think of traditional measurement error methods. And we've done some work here where we've extended these measurement error methods to handle multiple errors in multiple variables, both in the outcome and the exposure. And I like what we've done here, but really I feel like we sort of hit a ceiling using some of these traditional measurement error methods. They weren't able to. We're having a hard time extending them to errors in lots of variables, which is what we see when we use electronic health record data. There are full likelihood approaches which are very efficient, and so they're very they result in very narrow confidence intervals, and that they're very. I like them a lot, but they are computationally challenging, and they're also not fully developed for some more complicated settings. Multiple imputation is another approach which I really like, and we've used it many times. The basic idea is you have complete data for the subset that was fully validated. You're missing the validated data for the larger group. And so you build a model for the validated data in this subset, and then you multiply impute what you think the validated data would be based on your imputation model for the larger cohort. And then you do the analysis, you repeat it multiple times, like in typical multiple imputation. There are some complexities with that approach. Fitting good imputation models is the biggest challenge, and the method only works if you fit good imputation models, essentially. And there's some other things that make this a little bit challenging, but I do like this imputation approach. But what I'm going to focus on today is something called generalized raking. It makes fewer assumptions than multiple imputation, so it's a more robust approach. Typically it results in slightly wider confidence intervals than multiple imputation because you're making fewer assumptions. But it is a fairly good approach. And my experience is most people are not familiar with generalized raking. So let me just quickly go through the basic ideas of generalized raking. And this is using a simplified example. So let's suppose we're interested in estimating the prevalence of childhood obesity, which I'm labeling with D. So D is 1 if a child has obesity, 0 otherwise. And D is really only known in the subset that are validated, in this small subset. What we do know D star, that's an error-prone measure of childhood obesity for everybody in the electronic health record. So you could imagine, let's estimate the prevalence in the entire population, defined by those in the electronic health record, using an inverse probability weighted estimator based on the fully validated data set. So all that is you're upweighting the prevalence in this group to represent what you think would be in the larger population. And IPW estimators they're known to work well. They result in unbiased estimates as long as the data are missing at random, which hopefully you chose which records to validate, and so the missing at random assumption holds. And as long as every record had a non-zero probability of being sampled, then you'll get an unbiased estimate for the prevalence that you're interested in. But IPW estimates are known to be quite variable, to result in wide confidence intervals. So there may be a way to improve on them. Now you could think of also, let's suppose we wanted to do an inverse probability weighted estimate of the prevalence of D star. So you could do that. You could apply those same IPW weights to estimate the prevalence of D star in the whole population. But you actually know that prevalence because D star is available for everybody. So your IPW estimate is going to be close to, hopefully, the true overall population estimate, but it's not going to be exactly the same. Now you could imagine tweaking your inverse probability weights such that your IPW estimate for the prevalence of D star is exactly equal to the known prevalence. Okay, so you keep your weights as close as possible, but under the constraint that those prevalences, the estimated prevalence is equal to the known prevalence. And now with these new weights that you got, you can apply them to the original. What you're really interested in is the prevalence of D. So you can then apply them to estimate that prevalence of D to obtain a new estimator, the generalized raking estimator for the prevalence of childhood obesity in the population. Now, if D star is correlated with D, which it should be, I mean, it's the error-prone measure, then your new estimator, your generalized raking estimator, will be more efficient than the IPW estimator. It'll be a better estimator. And so that's the basic idea behind generalized raking. You slightly change your inverse probability weights using auxiliary data that's correlated with what you're really interested in order to improve their efficiency. And we'll show you this in our applied example in a bit. But that's the basic idea. As I said, generalized raking is more efficient than IPW estimator, but it makes the same assumptions, which are fewer than multiple imputation or likelihood-based approaches. This idea extends to more complicated estimators. So on the previous slide, I just showed the prevalence, but let's say we're interested in a regression coefficient, which is what the example will be. The auxiliary variable is actually the influence function, and I'll show you that in a bit as well. But the same ideas apply. This generalized raking is pretty well known in survey sampling literature, but it's less well known in biostatistics. It's also referred to sometimes as generalized regression or calibration, and there's a few references there. And something that's important to note is generalized raking estimators converge asymptotically to augmented inverse probability weighted estimators, AIPW, which many of you may have heard of. So this is another way of fitting an AIPW estimator. Okay, the last little bit of statistical background that I wanted to go through is designs for sampling validation records. So you could imagine so for sure you want to randomly select or use a probabilistic sample to select records for validation. And the simplest way to do that is simple random sampling, where every record has an equal probability of being sampled, and you randomly pick some and then proceed. That works okay, and it works well, but it may not result in a very efficient sample. For instance, let's say we were interested in a rare outcome. Childhood obesity is not rare, unfortunately, but let's say it was. Then it's possible if you just did simple random sampling, you would not get very many children in your sample with childhood obesity, which would limit the efficiency of your estimates. So case control sampling is a more efficient approach. So you could sample half of your sample being those with childhood obesity based on the EHR, half without, and then that will give you more childhood obesity numbers and therefore a more efficient estimator. And there's various versions of this, like balanced case control sampling. There's also been recent work on optimal sampling, and some of this is by our group. Just a few things to highlight. The optimal sampling design depends on the analysis approach, and the optimal sampling design also often depends on information that you don't know about until you've actually done some chart reviews, until you've started doing some validation. And this leads to something called multi-wave sampling, where you divide up your validation into different pieces. Like the first wave, you may do a simple random sample or case control sampling, and you learn information, and then that information that you learn, you then apply to then decide, well, what's the optimal sampling design? And then you apply that, and then you then target the optimal records for sampling in the second wave. And we'll go through the details of that also in our example. Okay, I hope that statistical introduction was somewhat clear. I understand we're holding the questions till the end. This is where I'd probably pause and stop and have everybody ask the things that they're confused about, but I guess I'll hold off on that and I'll just continue. So the next thing is I'm going to go through our experience designing and carrying out a multi-wave validation study. We are interested in the association between maternal weight gain during pregnancy and the time to childhood obesity. So that's our question of interest. Our secondary question is, what is the association between maternal weight gain during pregnancy and a child's risk of developing asthma? We're not going to talk much about the secondary endpoint, so we're mainly focusing on the first one, but just to let you know. Okay, our study variables are going to be Y, the time from birth to childhood obesity or censoring, D is the indicator of childhood obesity. X is maternal weight change during pregnancy. And Z is going to be a set of other covariates that we're going to adjust for as potential confounding variables. So what we have in the electronic health record are the unvalidated variables. So they are error prone, and we denote those with a star. So we have Y star, D star, X star, and Z star. And again, we have that for everybody in the EHR, but we'll only have Y, D, X, and Z what we're interested in for those records that are validated for a small subsample. Now, our goal is writing this as a statistical model. We'll use a Cox regression model where we're interested in this beta coefficient. So that's the coefficient that's associated with, it's going to be a hazard ratio or a log hazard ratio associated with an increase in a maternal weight gain during pregnancy and its association with childhood obesity. So beta here is our parameter of interest. We have other confounding variables and their associations, but that's of secondary interest. Our phase 1 data, we often, in this statistical literature, we often refer to the electronic health record data as phase 1, and then the subsample that are validated as phase 2. So our phase 1 data, we have, again, Y star, D star, X star, and Z star for everyone. Now, and everyone is people meeting the following inclusion criteria. So it's mothers at the Vanderbilt Medical Center who are in the electronic health record who gave birth between December of 2005 and August 2019. And they also had to have a linked child whose data were also in the VUMC electronic health record. The mother had to have at least one height measurement and one weight measurement within a year and 3 quarters prior to up to the date of giving birth. So time 0 is the date of birth. The child had to have at least one pair of weight height measurements after 2 years. We define childhood obesity as happening after 2 years. So they had to have a measurement after, at least one pair of measurements after 2 years. So from this inclusion criteria, we had 10,335 mother-child pairs. And then we extracted data by programmers. We gave a little, they charged us a little fee. And so we asked programmers at Vanderbilt to extract this data for us. And they gave us demographics, ICD-9, ICD-10 codes, labs, encounters, insurance data, et cetera. And then we tried to do our best to create these variables using the electronic health record. We used published fee codes to determine different outcomes such as asthma, diabetes, and depression, which were used as covariates. We defined childhood obesity using BMI greater than 95th percentile based on age and sex using CDC growth curves. And we also did some data quality checks as well based on some published ways of evaluating outliers for different weights and heights. Now, our exposure of interest is maternal weight gain. And this is, we'll define that as the average maternal weight change per week during pregnancy. That's somewhat simple, but this was thought to be a nice, simple summary to do for our first analyses. And so really this is defined as the weight just before delivery minus the weight at conception divided by the length of the pregnancy. Now, the challenge is even in the best of situations, we often don't know these variables. So what we did is something, we estimated the trajectories of mother's weight gain using functional principal components analysis. And you could dedicate a whole talk or two to this FPCA, the functional principal components analysis, and I'm not going to. But the essential idea is it borrows information from mothers while fitting a mother-specific weight trajectory for each mother. And we're following a procedure published earlier in JASA. And we also, initially, we did not have the estimated gestational weight, the estimated length of the pregnancy. And so we assumed that all pregnancies were 273 days initially for our initial pass, because that wasn't something that was easily extracted from the electronic health record. by the programmers. So using this little figure at the right, this is an example of a woman's weight gain during pregnancy. I changed 0 actually here is referring to the estimated date of conception. And so the estimated weight change would be, okay, the estimated weight at a delivery, right before delivery, minus estimated weight at conception based on the functional principal component analysis estimate divided by 273 days. And I think we're doing this per week, so then we multiply that by 7. So that's our initial estimate for maternal weight gain, our covariate of our exposure of interest. Okay, so that was the electronic health record data. And let me just talk a little bit about the validation procedures to get our phase 2 data. So this is how we went about validating data. So this was done by a thorough review of the complete electronic health record by a research nurse. We had enough money to validate approximately 1,000 records, and these are 1,000 linked mother-child records. The phase 1 data was extracted computationally. That's important to note. But this phase 2 data involved looking at the entire electronic health record by hand. And so she was able to read through the free text fields and look at other things that were not easily extracted. So for example, estimated gestational age was not in the phase 1 data that was extracted by the programmers, but she was able to find it in the medical records. And so she was able to include that as a variable by doing the chart review for this 1,000 records. So she entered things into REDCap forms or Excel spreadsheets, depending on the variable. We did a pilot of the validation process of 10 records. And from the pilot, we realized that there were too many weights and heights to validate all of them. That there's, after you're validating like 70 or 80 heights and weights, it's more likely you're going to make an error in the validation process than there's actually an error there. And so we came up with a way to choose a subset to validate. So we chose key weights and heights to validate, and then we also flagged some that we thought were outliers for validation. So here's a screenshot of the REDCap form, or part of the REDCap form. And so really it's the research nurse went through and essentially, you could almost say, did double data entry. So she re-entered the data. Here's an example of flagging for outliers in weights. So this is actual data. It's been date shifted, so it's de-identified still. But this is what we received in the EHR. And you see that there's, this is the functional principal component analysis estimate of the trajectory, and then this is the 95% confidence bands. We flagged all weights that were outside of the bands, which correspond to 5 in this plot, and we had her look through those. And in this case, the chart reviewer found that this was an error, kind of obvious now by looking at the plot, and these ones were correct. And so then the FPCA was refit to get a new trajectory. It was also discovered that the length of the pregnancy was estimated to be 259 days, so instead of 273 days. So that was used to come up with a new estimate for the weight change during pregnancy. Okay, so that's the validation procedure. I'm going to spend a bit of time, though, on the statistical issues, which are how do we select which records to validate? And so I touched on that a little earlier, but now we're going to go through it in detail for this specific study. So with fixed strata and a fixed number of records to validate, in our case, 1,000, the optimal way to validate across strata for an inverse probability weighted estimator is using Neyman allocation, which is based on the following equation. So N is the number we're going to validate, 1,000. NS, capital NS, is the number that are in the strata in the population, and sigma S is the standard deviation of what we're trying to estimate within that strata. So the number that we should sample from the stratum is proportional to the size of the strata and the standard deviation in that strata. And now if we're interested in a regression coefficient, so in our case, we're interested in the hazard ratio or a log hazard ratio, sigma s is actually going to be the standard deviation for the influence function for beta. Okay, so that's what the standard deviation will be. Now, the choice of strata matters. It's good to choose strata to minimize this standard deviation within, but maximize between. And so generally more strata are better, and optimality is achieved when you have equal numbers in each of those strata. However, sigma s, the standard deviation of the influence function for beta, is generally not known. So what we do is we approximate sigma s using an estimate from the electronic health record data, using some, we'll call it sigma s star for the first sampling wave. And then once we get that, we'll re-estimate, once we do our first wave of sampling, then we'll re-estimate sigma s based on that first wave of validation, and then we'll calculate the optimal allocation from that. So let me show you in practice what we did. So defining strata, the variables that are going to have the largest influence on our parameter of interest are going to be the outcome variable, so the time to event, the actual indicator of the event, and then the exposure of interest. And so we define strata based on these, on the error-prone versions of those variables. And we're going to want to oversample records from strata that will have the largest influence on beta. And the ones that will have the largest influence on beta are things, if you think intuitively, it's children who have obesity early. So D star equals 1 and Y star small. Those will have a lot of influence. Or those with a lot or a little weight gain. So X star extreme values will also have a lot of influence. And the standard deviation of the influence function will likely be large within strata that are defined based on in extreme values in these, based on these variables. So I'll show you in the next slide which strata we actually use, but we're basing it on Y star, D star, and X star. And what we do is we fit a Cox regression model, the analysis model, to the error-prone data, and we get an initial estimate of beta star, and then we're able to compute the influence function for beta star for each observation. And then we use that variance, so we use that influence function to play around with different strata boundaries. So remember, there's an electronic health record data here, and we can decide which strata we want for sampling. And so we play around with the different strata boundaries using the known, or the estimated influence function, and then the different sizes based on how big the strata are. And we play around with those so that we end up figuring out how many we would sample based on a certain stratification from each strata. And we want to do it so that those are approximately equal across strata. So the S designates the strata. Actually, my notation is kind of bad there. I won't talk about it. The 1 here is designated, this is our first wave of sampling. And these should all be 1s. And this should be S is 1, this S is 2, all the way up to big S, the number of strata. Okay, let me show you what we did. So we ended up in our original strata having 21 strata based on, again, obesity, error-prone levels of obesity, the follow-up time, and maternal gestational weight gain estimated using electronic health record data. And so these are the different strata that were chosen, and this is the number that's in each of those strata. And then using name and allocation based on the estimated standard deviation of the influence function, this is the number that we decided to allocate to each of those strata. And we decided for our first wave, we were going to sample 250 records. Because of rounding, we ended up sampling 252. Now, you notice these numbers are not exactly the same, but they're approximately of the same order. It's really hard computationally to get them exactly the same, so we felt like this is pretty close. And so this is our first wave of sampling. So we then selected 7 records out of these 190 based on these values, and then Shannon, our chart reviewer, went through and did data validation for those 7 records, and she went through and did it for all of them. And that was our first wave of validation. So a couple months later, once that validation was done, we got all the validated data, and then we fit a new Cox regression model incorporating the validated data. So this is just a weighted Cox regression with the validated data. And we got a new estimate of the standard of the influence function for every observation. And then we're able to calculate the standard deviation of the influence function for each of the strata. And then we were able to, and then what we did is we used name and allocation to select how many we should sample from in our wave 2. So this is our name and allocation formula. This is, so we, N1, N parentheses 1 is going to be the number that we sampled in the first wave total, the 252, and we decided to allocate another 250 to the second wave. So this is 500 approximately. And then again, this is the number in each of the strata and the estimated standard deviation of the influence function in each strata. And then the number to sample in wave 2 is going to be that number minus the number that we already sampled in the first wave. And this is the optimal sampling allocation for an inverse probability weighted estimator, which is very close to the optimal for a generalized raking estimator. Now, in some cases, this N2S is actually negative because we sampled more from a stratum in the first wave than we actually needed to, based on our new estimates of the standard deviation of the influence function within that strata. So if that happened, then we closed that strata and we redid the name and allocation with smaller numbers of strata. Let me go through and show you an example of this. So these are our first 5 strata. Now, name and allocation for the second wave suggested a fairly different sampling scheme. So name and allocation for stratum A was 6, but we actually had already sampled 7. So in this case, we closed that stratum. Name and allocation for stratum E was 105, and we only sampled 16. So we really undersampled from that first wave, from that stratum in the first wave. And so we, what we ended up doing is splitting this stratum E for the second wave so that we'd sample more from it, but dividing it up among different strata. So in the end, our first wave of sampling was not as good as we had hoped. And so we ended up closing 9 strata, and then 4 strata we actually split. So for example, with those first 5, you can see we closed stratum A. So the second wave, we didn't sample anybody from that, validate anyone from that chart, or sorry, from that stratum. And then for stratum E, we ended up dividing it into 3 strata and sampling 22, 15, and 18 from each of those strata that were calculated from it. So after the second wave, we'd validated 500 records, and when we repeated the process. And we had a third wave of sampling where we did 125, we allocated up, and then we did a fourth wave with 125. So we had 750 in the end that were targeted towards our obesity endpoint. And this is, again, the original strata. You can see that even after, across all 4 waves, we never sampled again from that first stratum, strata A. And stratum E ended up being divided into 1, 2, 3, 4, 5 strata in the end of the day. Anyway, so that was the process we went through to try to get an optimal or a near optimal sample for which records to validate. We also did this for the asthma endpoint. I'm not going to go through the details of this, but it was very similar. There were 250 records that were targeted for sampling for the asthma endpoint. Anyway, we started with 5 strata and we ended up with 10 strata. Each stratum was divided into 2 in the end. All right, let me spend a little bit of time and just show you some of the results from this. So these are, in this table, I'm showing you essentially all of the variables, the key variables that were used in the analysis. We have the endpoints and then the key exposure, and then we also have the covariates that we adjusted for, and then also child asthma and maternal asthma. That was for the secondary endpoint. The first column here is the phase 1 data. So in our phase 1 data, 18% of children had obesity. In our phase 2 data, 42% had obesity, but that's because we oversampled records with obesity because they're more informative. But if you actually compare the 996, their EHR data with their validated data, the percent error was quite low for childhood obesity. Only 0.6% had an error. That's a positive predictive value and a negative predictive value, which is greater than 99%. You can go through and look at the other error rates. So the time to event or censoring, there was about a 5% error rate in that variable. Given that there was an error, the median error was about a year off with that range given there. Maternal weight gain, that's our exposure of interest. 100% of records had errors, but a lot of these were very small errors. As you can see, the median was really close to 0. The range was never huge, although those are some errors. And there is some discrepancy there. And a lot of these errors were due to the estimated gestational age. Remember, we assumed initially it was 273 days, and we were able to actually get it from the chart review. And then you can go through and look at the other variables and see their error rates. Maybe just notably, some of the higher error rates, maternal depression, 13.5% were in error. Private insurance status, 24% in error. Smoking status of the mother, 12% were in error. Childhood asthma, which is our secondary endpoint, about 10% in error. And the positive predictive values and negative predictive values are given there. So I realize that's a lot to digest at once, but that's anyway, that's comparing. It shows you the error rates between our phase 1 and phase 2 data. This next slide shows the log hazard ratios for childhood obesity, and I'll explain these a little bit more in the following slide. But let me just focus on this first one, this first row. This is maternal weight gain. That's what we were interested in. Our beta coefficient estimate, if we use just the electronic health record data, is 0.87, a standard error of 0.18, so a small standard error. If we did an inverse probability weighted estimator, we get something that's a little bit stronger of an association, a much larger standard error, because IPW only uses the validated data. Our generalized raking estimator, we get a beta coefficient estimate, which is kind of in between the two. And this standard error estimate is smaller than that for the inverse probability weighted estimator, which we expect by theory, and also because of our sampling strategy. However, it's not going to be as small as if we just analyzed all the phase 1 data and assumed there were no errors. So scientifically, what this means is, holding all other factors constant, a child from a woman who gained 250 grams more per week during pregnancy, which corresponds with 10 kilograms in added weight over a 40-week pregnancy, that woman had an estimated 30% increased hazard of obesity of the child. That woman had a child who had a 30% increased risk or hazard of obesity before age 6. So our hazard ratio is 1.3. There's our confidence interval. And this is using our generalized raking estimator that incorporates the data validation. Now, of course, you might wonder, well, what would we have gotten had we just done it on the original phase 1 data, ignored all this validation process? And we would have gotten an estimate which is quite similar, a hazard ratio of 1.24. Here's our 95% confidence interval. So it's very similar. We did do secondary analyses which showed differences between what we would have gotten had we just used the electronic health record data versus what we got using our validation procedures. So in an additional analysis, raking the naive influence function suggested that the relationship between maternal weight gain during pregnancy and childhood obesity was nonlinear. And so a strong nonlinear association with a fairly constant hazard of obesity for women who gained under 11 to 12 kilograms during pregnancy, but increasing hazards thereafter. And if we just use the phase 1 data alone, we did not see that nonlinear association. So here are the hazard ratios comparing everything to a woman who gained 0.2 kilograms per week, which is just a little bit less than the median weight gain in our cohort. And so you see hazard ratios for childhood obesity are fairly constant, but then for women who gained quite a bit more, their children had a much higher risk of having childhood obesity. And here's visually that association that we saw using the validated data, but we did not see any association, any nonlinear association at all using the unvalidated data. There were a couple other things to point out that were different. So in the childhood obesity analysis, remember in private insurance or insurance status was very error prone. 24% had errors. So if we use the just electronic health record, we got a hazard ratio of 1.2. If we use the validated data and our procedure, then we got a hazard ratio, a much stronger association, 1.8, with non-overlapping confidence intervals. For our childhood asthma analysis, that was the secondary analysis. We had a 10% error rate for that variable. Weight gain was associated with a borderline potentially protective effect using the electronic health record data alone. But if we use generalized raking, we ended up with something that was clearly much more null. All right, just to wrap this up, to my knowledge, this is really the first multi-wave validation study that's attempting to follow some optimal sampling procedure. And so I'm happy with the work that we did. I feel like the majority of electronic health studies do not validate data, and there's a small subset that do validate data, but they don't. They're typically validating suboptimal records for chart review, and very few properly incorporate the validation data into analyses. Often they just do it and they perhaps report that. This was a lot of work, and as you may imagine, and it was hard to keep track of the different validation data sets, how many we were going to sample from each strata, et cetera. And so we actually developed an R package, Optimal, which helps make that easier. And this was really led by Jasper Yang, working with Pam Shaw. So kudos to him. As you saw, we conclude that maternal weight gain during pregnancy is associated with childhood obesity. I know you're all thinking this, and I think this is a lot of work that we just did to come up with the same conclusion as we would have gotten if we just done the naive analysis. And that's true. I would counter by saying, well, you don't really know that until you do it. And there's plenty of situations in the literature and in my own work where I've seen differences, but this is just not one of those, the way things turned out. There are, of course, limitations with what I've presented here. The validated data are not necessarily the truth. That's clear, and I need to say that again. The validated data are not necessarily the truth. We believe they're closer to the truth than the original electronic health record data. And so what we can think of is we are estimating what we would have gotten had we validated all of the records, but that may not be the exact truth. And of course, there's other challenges with using electronic health record data, confounding, erratic data capture, missing data, et cetera, which I haven't really addressed here. There's definitely a lot of room for future research, which we're excited about. There are other analysis approaches. It would have been fun to see what we would have gotten had we done a multiple imputation estimator or applied some of our semi-parametric likelihood methods to this. We're also studying optimal validation designs when you have multiple parameters of interest. So if you recall, here we had obesity as an endpoint, and then we had a secondary endpoint of childhood asthma. And we just sort of arbitrarily did an optimal sampling design of 750 records for the obesity and 250 for the asthma. But I think there's a lot of potential for better ways to think about that, of how to allocate samples across multiple parameters of interest. And I just want to say that we're also actively involved in several other ongoing validation studies and multi-cohort HIV collaborations throughout East Africa and Latin America, where this is also a big problem and a big challenge. That's all I have. Thank you very much. I hope this was of some interest to you.
Well, thank you, Brian. This was an excellent overview of your really elegant work, which is solving a real need for improved validation studies. So thank you for summarizing it so eloquently. I really appreciate it. I just want to remind folks that this floor is now open for questions. So if you think of any, please paste them in your in the Q&A feature, and we'll be happy to address them. So I see one question already. So Ryan Hickson asks, could you foresee any machine learning approaches that could improve efficiency of this sampling, multi-wave sampling? For example, only needing 2 rounds versus 4 or something like that. Have you thought about this?
Yeah, that's interesting. I have thought of machine learning, especially in the context of multiple imputation, where you're building an imputation model based on your validated subset, and then you're wanting to, so you want to have a really good model there that's very predictive of what you would have gotten had you validated everything. And so that's a direction that we're going. As far as limiting the number of validation waves, I'm not sure about that. I haven't thought about that at all. You didn't ask this, but one other comment is, I think we may have done more waves of validation than needed in this study. A lot of our simulations suggest you could do 2 waves of validation, and that works pretty well. You divide the first half as your first wave, and then based on your first wave, do a second wave. Maybe we were trying in this case because we were doing it in real life. We really wanted to do it well, but in general, I think we could have just done 2 waves anyway.
Thank you, Brian. That makes sense. So I have a question of my own as people are thinking of other questions. So it's super interesting. The phase 1 where you are only using computable information from EHRs, just using some types of codes. So in this case, you use phi codes, but there are, of course, other ways to do that. So I was wondering what impact might your decisions have around how well you capture those variables in the first phase. So meaning that you can prioritize specificity versus sensitivity using different types of approaches to capture that information. And I was wondering if you had any intuition on what should you be prioritizing for the phase 1 identification of your variables, the error-prone versions.
So you're suggesting maybe we can do a really good job of capturing phase 1 data for certain variables and potentially avoid having to do validation, or maybe minimize the validation or something. Is that the idea?
Yeah. So there are many ways, as you can imagine. You can identify variables from EHRs, and some are better than others. So if you, for example, there are some common sense approaches like requiring 2 codes, for example, requiring a drug and a medication, or a drug and a code to define a condition, which would logically have higher PPVs or more validity in the first phase. So I was wondering if that has any impact on your kind of the entire pipeline.
Certainly. So yes, if the phase 1 data have very few errors, then there's less room for bias of your original analyses on that phase 1 data, and so you may be able to get away with not doing as much validation, or maybe not even any at all, if you really trust those variables. There's also the other extreme. If you have phase 1 data that are so poor that sometimes you don't gain much by incorporating that into your analyses. Like we've done these sort of combining the validated with the unvalidated data, and so there's a little bit of a sweet spot where these methods can be used, although we think it's a big sweet spot. But if you're error prone, if your data initially are so error prone, then you may as well just analyze the validated data. And then if your error prone data have so few errors to begin with, then you're often going to be better off. You're going to have more precision and maybe just a little bit of bias, but a little bit of bias that you're willing to live with by just analyzing the phase 1 data without doing the chart reviews. Does that answer your question?
Yeah, that's very thoughtful. Thank you. So we do have one question that came in through the chat, which I'll read it for you, Brian. So Wei Hua asks if there are any ways or intuitions to interpret the discrepancy you find between this analysis and the analysis that is based on just the chart review data only. What do you think is the gold standard, and how would you approach this?
Well, if I understand the question right, the first part, so we do believe we wouldn't call it a gold standard, so we call it a reference standard for our situation, where we believe that the validated data are of better quality. And so as far as differences between interpretations, we think we would interpret the validated data and the results using the validated data because we think that's of higher quality. So that's what we would do. Again, I don't think there's a gold standard here because we don't know the truth. We're using validated data, which may have some errors. In our simulations, we can create gold standard data and we can see, okay, what's the impact of these approaches? And so, yeah, I'm not sure I answered your question, Wei, but those are my thoughts, at least from that. Okay, thanks.
Thank you. So I have a follow-up, Brian, on something that you were mentioning towards the end. So as you said, the total sample for validation that you had here was 1,000 patients or 1,000 observations. And it seemed like that was not based on any kind of data-driven way. It was based on more the resources that were available to you, if I got that correct. Okay, so I was wondering if this method has can play along with some of these prospective Bayesian type approaches of validation sub-study designs. Are you familiar with those, and have you thought about that, where you can basically prospectively calculate your PPVs and NPVs as you are going through these and determine at which point your validation efforts are futile because they cannot improve your PPVs above a certain threshold that you decide on a priori basis. So I was wondering if there is any way to kind of approach it from that lens, rather than coming up with a number, let's say 1,000 to begin with. Just do this prospectively and see how it goes.
Yeah, that's interesting. And I'm not familiar with those papers. So Rishi, maybe if you don't mind, after sending me a paper or two on that, because I'd like to learn more about it.
Sure, yeah.
You're right. So there's one way to think of that, like beforehand, what sample size do I need for validation to get a certain level of precision? And we thought a little bit about that, but it's pretty complicated because it has to do with, because we're dealing with errors in lots of different variables, and it has to deal with the magnitude of those errors. We don't know what those are, and they could be correlated. So although we thought a little bit about it, we haven't gone too far down that path. But I like the idea of maybe sequentially going through it, like you're saying, and that, like, maybe after doing, if you did have a lot of money, but you don't want to waste it, of course, maybe after doing a 500, you say, well, what's our estimated value added in terms of precision by doing another 500, and you can decide, well, it's not worth it. And I don't think there's anything you need to worry about, like preserving the alpha level like you would in a sequential trial for that. So that's a very interesting direction.
Yeah, and resources is, of course, one constraint. The other constraint, which is more important for Sentinel, actually, is time, right? Because you are working in a situation where you need timely evidence or almost in real time for safety signals that are coming up. So anyway, so I'll definitely send you those papers. But thanks again. I don't see any more questions that are popping up. We are close to 1 o'clock. So Brian, I really want to thank you again for taking the time and really congratulate you on this excellent work that you presented today. As a reminder for folks online, this session has been recorded and will be made available through the webpage, sentinelinitiative.org. You can also find details and registration links for future seminars, and we have some exciting ones coming up through the summer and the fall. So hopefully we will see some of you there as well. And so this concludes our session. We hope to see you again next time. And thanks again, Brian.
Thank you very much, Rishi, and everybody else. Take care.